Alright, so in this video I want to talk about how we can approach simplifying radicals. This can be very tricky sometimes. There are two main strategies in which you can do this. One of them is less work, but it's more helpful if you know your factors and you know your times tables and really well. And the other one does take, I'd say, more work. It's a longer process, but it's easier to apply when you have larger numbers. So let's talk about the first one. That's using a factor tree. And then afterwards, I'll leave space for our other method, which is prime factorization. And so first, factor tree. Let's use an example. Let's go ahead and do root 32. If you're quick and you know, some nice factors that work out here, you might be thinking, okay, what about 8 and 4? That might work out, right? You might break that down, this 8, into even more numbers, because the goal here is also to question yourself and think, okay, can I break this down into factors that might have a square root? Are they a perfect square? Like, is this a perfect square? And if not, can I break this down so we could square root into something? And so you might ask yourself, okay, you know what? I can break this down into 4, into 2. Keeping track of these 3, right? This isn't suddenly lost over here. We are still keeping it around. So I'm actually going to bring that down. And then you're like, okay, cool. I can go ahead and see some perfect squares. I'm going to square root those. This turns into 2. Bring down my lonely root 2, which doesn't, break down. And then this other one also goes into 2. Combine those coefficients, multiply them out. So you're left with 4 and your lonely root 2. And that's as far as you simplify, right? That is the factor tree method. That is me drawing these. These are kind of like your branches, right? You go from top down. You might have, known your times tables higher and done this quicker. You could have looked at this problem and said, you know what? I actually know that 32 has factors of 16. Noticing, right? I'm always keeping that root when you break things down at first. Don't square root them until afterwards. But okay, 16 and 2. This is faster for me. This is a perfect square, and it square roots to 4. And can't do much else. Just kind of squeeze these together, and you got there a lot faster. Right? And that's nice, once again, when you know the factors, when the number isn't necessarily a really large number. But I'm going to show you the longer way, but a really effective way if this number happens to be larger and you're like, oh shoot, I don't really know my factors right away. First thing I want you to notice is that word prime. That is referring to prime numbers. We learned these in elementary school. They're numbers that can only divide into themselves in 1. I like to remind students that numbers we can use when it comes to this method are 2, 3, 5, 7, 11, usually. It could go higher. Obviously, there's a lot of prime numbers. But these are helpful in using this process. And so we'll use the same example we did for the factor tree. So I'll go ahead and write this radical of 32 with this radical of 32. And so the first thing you have to do is, you may choose any of these, but it's best to start with the lowest prime factor to test out and use to divide this. Meaning, okay, I'm going to use 2. Now it looks like long division. It's kind of what we're going through. Do that process. And then you might be thinking, oh wow, isn't that the 16 and the 2 from earlier? If you use prime factorization and you notice, that you can separate these 2, and you're like, I know that's going to break down into, that's a perfect square and I could square root that. You could do that method. but I'm actually going to ask you to keep going. Your goal is to keep going until your final answer is 1, and then I'll explain what happens. So I'm going to bring along 16, and now that's under, and I'm going to go ahead and use 2 again, right? I'll only go higher if it doesn't work out on top and it doesn't give me a whole number. If this was like a decimal, I would be like, whoops, 2 doesn't work. Let me move on and try 3 now. If that doesn't work, whoops, let me move on to 5. But 2 is always really nice, especially if you can tell that, you know, these are even numbers. They'll most likely than not, you know, divide by 2. This gives me 8. Bring down the 8. Divide by 2 again, that's 4. Just going through this whole process until you finally hit 1. Nice, I got 1. Now what, right? I want you to take into account, what color should we use for this? I want you to focus on the prime numbers you used. This is actually another way of how you broke down 32. And so I used 1, 2, 3, 4, 5 2s. Okay, what you do with this? Actually, let's do that different. Oh my gosh, there we go. What you do with this is you rewrite them all with radicals. I used 1, 2, 3, 4, 5. We have just gone from radical 32 and broken it down to this. That is much easier for us to look at, and you can start grouping. What I like doing with these, especially if you have the same radicands, which all of these do, pair them up, because when you pair them up, you will be able to afterwards see that they're perfect squares and square root them, right? So noticing that this pair gives us root 4 and breaks down to 2. Can't forget about that multiplication there. Can take this group, root 4, nicely breaks down to 2, and then we have a lonely one, and we know that it's not a perfect square. Bring them all the way down to root 2, and look at that. We get to our same answer of 4 root 2, and we've fully simplified. And so, yes, it's a lot more work to have to do this, but it looks a lot nicer. It's easier to kind of see how you can group things and still get to your simplified version of your original radical. And so before I end this video, I'll show you one more time how you can use prime factorization for maybe a larger radical than 32. And so I think an example that would work great here maybe is, I'll scroll down. Let's go ahead and use, let me zoom out a bit. There we go. Let's use root 162. And on the side, I'm going to remind myself of my prime numbers, right? It's like I said, it's important to remember those because they're useful for this process. And so I'll easily start with 2. I'll work through that. You know, that's 81 if you work through it. Not done. I now have 81. I know that it ends in an odd number. It's not going to be divisible by 2. So I move on, and I'm going to use 3. And so, okay, we're like, oh, that goes in twice. It's 27. Moving on. Now working with 27, not divisible by 2. Going to try out 3. It's nicely 9. Going down until we finally get to 1, right? Actually, let's keep that in this color. And I got to 1. Nice. Paying attention to the prime numbers we used. And so this time we used 1, 2, and we used 1, 2, 3, 4 3s. Gonna take all of that and rewrite it, right? We started with root 162, and it's now going to be 1 root 2, and we have 1, 2, 3, 4 3s that we used, keeping the radicals because we just broke that down. And like I said, look for where you can group in pairs when you have the same radicans, right? We have 4 of them, so we can take these 2 groups. These 2 become root 9, which is a perfect square, and it turns into 3 without that radical. This also groups to root 9. Let me bring down that times. Breaks down to 3. And then we have our lonely, root 2, which can't break down anymore. Let me write that nicer. And then we can go ahead and multiply these together. That gives us 9. We have the root 2, and you can rewrite this and flip them, right? I'm just going to flip the order. And so that's 9 root 2, right? Always question, can I break this down more if you have a radical somewhere? Can I break it down? We can no longer break it down, and so we've gotten to our answer, right? If you were someone that wanted to use the factor tree and you just know your times tables like that, you could have used a shortcut here at the beginning, right? Kind of using prime factorization and also using the factor tree together. You could have started here at 162, use that, but notice that 81 is a perfect square. And what you could have done, and I'll use this in a green, is taken these 2, also write them in roots, right? So 81 and the 2, and then broken it down from there, right? And so there's ways to combine these 2. But if you're ever just like, I need to fully break it down because, I'm not as familiar with what perfect squares look like. I don't know them all really well. Use prime factorization. Use the whole process. You'll still get to your answer, and you could feel even more confident about it. But if you notice the shortcuts, use those shortcuts. Those work too. All right, hope that was helpful.